Hello everyone, thank you for listening to my virtual talk for ICPP 20. My name is David Williams Young, and I am a postdoc in the Scalable Solvers group at Berkeley Lab in Berkeley, California. Today I'm going to be talking to you guys a little bit about some of the recent work that we submitted to ICPP 20 on parallel shift-invert spectrum slicing on distributed architectures with GPU accelerators. Parallel shift-invert spectrum slicing is a novel eigensolver approach, and the approach that we take is specifically tuned for the self-consistent field, or SCF, type eigenvalue problem commonly encountered in electronic structure calculations. As this is an applications paper, before delving into the specifics of the method that we presented in this work, I want to give you a little bit of a background on this method from an applications perspective. In contemporary software implementations of density functional theory, are more commonly referred to as DFT. The computational bottleneck is the self-consistent determination of the so-called Fock matrix, which is labeled here as F, which depends on some subset of its own eigenvectors, which is labeled here as C0. In essence, the self-consistent field loop consists of repeatedly forming the Fock matrix with some previously known set of eigenvectors, solving a linear eigenvalue problem with that Fock matrix to obtain some new set of eigenvectors, and checking whether or not the span of the desired subset of eigenvectors has changed between SCF iterations. The bulk of the computational work required for the SCF procedure is contained in the solution of the linear eigenvalue problem at each SCF iteration. While both direct and Krylov subspace methods are often sufficient to solve a linear eigenvalue problem required in the self-consistent field procedure, obtaining further improvements on large computing resources, including those with GPU accelerators, requires explicit consideration of underlying details of modern computing architectures, as well as the structure of the SCF eigenvalue problem itself. Over the past several years, there's been an increasing reliance on the use of accelerators such as GPUs to perform the majority of the floating point operations for target applications on modern supercomputers such as Summit at Oak Ridge, as well as some of the next-gen machines such as Perlmutter at NERSC, Aurora at Argonne, or Frontier at Oak Ridge. As GPUs are capable of expressing much more concurrency than CPU-only machines, flops have really become relatively cheap compared to other operations such as communication. So the increasing use of GPUs in high-performance computing has exposed some bottlenecks which may or may not have been observable in CPU-only applications. With the understanding that flops are inherently cheaper than communication on accelerator-based architectures, we wanted to develop an eigensolver with minimal communication volume and as few synchronization points as possible to avoid the interruption of concurrency on the device. So about a year ago, we submitted a paper to TOMS detailing a reference CPU implementation of the so-called SI-SLICE method, which is a parallel implementation of shift-invert spectrum slicing specifically tuned for the SCF eigenvalue problem. It's also on archive, shown here on the identifier at the bottom of the slide. Most of the details of SI-SLICE are relatively GPU agnostic, so I'll briefly outline how the method works and would encourage those who are interested in other details to check out the archive paper for more details. The basic idea behind spectrum slicing is to partition some spectral region of interest into multiple domains, or so-called slices, such that we may obtain the eigenvalues in each slice independently from the other slices. Now I put independently here in quotations as some of the information has to be communicated between slices to remove the possibility of missing or duplicating eigenpair approximations at the end of the diagonalization. But as we'll talk about in a few slides, the SI-SLICE method aims to minimize the amount of data that needs to be communicated by amortizing the obtaining of eigenpair accuracy over the entire SCF procedure. We can usually think of these spectrum slicing methods as trading a significant number of floating point operations for less communication, either in the volume of that communication or the number of times things need to be communicated. The general scheme encompassed by the SI-SLICE method is a three-phase algorithm which exploits the convergent nature of the SCF procedure to amortize the cost of computing eigenvectors to high accuracy over the entire set of SCF iterations. The first phase is this cheap and replicated either generation or update of the spectral shifts which partition the spectral region of interest into independent slices. This step is largely GPU agnostic, and I would encourage any of those interested to check out either of the two papers which are shown here at the bottom left of this slide. The second phase of the SI-SLICE method is the application of the so-called shift-invert subspace iteration to obtain eigenpair approximations within a particular spectral slice. This is where the majority of the floating point operations are incurred, and I'll discuss the specifics of this algorithm in the following slides. One of the key hallmarks of the SI-slice method is that we only need a single synchronization between the execution and context, which compute eigenvalues local to each independent slice per SCF iteration. So this drastically reduces the number of times and the volume of data that needs to be communicated for the diagonalization at any particular SCF iteration. To obtain eigenpair approximations within any particular spectral slice, the SI-slice method applies a shift and invert spectral filter to amplify spectral components near a target shift and damp out those which are further away. And the way that we do this is through the application of the Shift-Invert SISUBIT iteration, which is shown here on the bottom right. There are four computationally intensive kernels in this subspace iteration, and the first is this triangular factorization, which is labeled here as TRF. This will produce either LU or LD triangular factors from our diagonally shifted system matrix. Given some initial guess for the k-dimensional basis from which we're going to extract our eigenvectors in the neighborhood of some spectral shift, we're going to perform a fixed point iteration of a triangular solve using the triangular factors produced in the triangular factorization, and an orthonormalization step which orthonormalizes the solution of these linear systems at each iteration. In the SI-slice method, we use the Koleski-QR method to produce our orthonormal basis at every subspace iteration to avoid uncommunication in a distributed setting. Once we've produced our local basis, we can then obtain a set of eigenpair approximations for eigenpairs near that shift through the Rayleigh-Ritz procedure labeled here as RR. The last step in this procedure, labeled here as disvalidate, is just a distributed mechanism to check whether or not we've missed or duplicated eigenpair approximations between independent spectral slices. The implementation of this is largely independent of the GPU implementation, so I would encourage those who are interested in the details of this procedure to check out our archive paper, which is shown here on the bottom left. In essence, the Shift-Invert SISUBIT iteration in the SI-slice method trades the problem of eigenvalue decomposition for many independent triangular factorizations and backsolves which may be performed in parallel. Despite the fact that triangular factorizations formally scale the same as direct eigenvalue decomposition, they admit a much lower prefactor and tend to admit much better strong scaling on large computing resources. In addition, linear solvers are able to exploit sparsity, unlike direct eigenvalue solvers. So we're able to use high-performance software implementations of sparse linear solvers such as SuperLU and Partitions to solve our sparse linear systems on large computing resources. Unfortunately, the use of the Shift-Invert SISUBIT iteration in the SI-slice method leads to many more floating point operations over direct eigenvalue decomposition, but the fact that these operations may be performed completely independently from each other for independent spectral shifts leads to better strong scaling on large computing resources in the end. In contrast to other Shift-Invert factorizing methods which communicate the entire set of vectors in between independent spectral slices, the SI-slice method only communicates the eigenpair approximations and residual norms in between independent execution contexts to drastically reduce the communication requirement of the overall method. In general, we only communicate on the order of M or on the order of K data for each individual spectrum slice. And as you can see here on the right, we have the strong scaling of the synchronization step, which is essentially just an MPI all-gather of the eigenpair approximation and residual norms, even for large processor counts and large values of K, even up to 1,000. This is still sub 100 milliseconds, so we can essentially approximate the synchronization step as being a negligible cost in the overall computation. Even without the use of accelerators, the reference CPU implementation of SI-slice has been demonstrated to exhibit linear strong scaling to large processor counts, yielding over 2x improvement over the state-of-the-art CPU implementations of direct eigensolvers in ALPA and ScalePack. At low processor counts, SI-slice is much more computationally expensive than direct eigensolvers due to the presence of redundant floating point operations at each individual spectral shift. However, in the strong scaling limit, we can see that as SI-slice scales linearly to large processor counts, we end up winning in the strong scaling limit by expressing massive concurrency in the distributed sparse linear cells by SuperLU. Despite the linear strong scaling behavior of these results, SISLICE does not scale to an arbitrary number of processors, in that we impose a fixed number of shifts per invocation of SISLICE. So maximal concurrency is achieved when each set of subspace iterations may be performed on a separate execution context. In the conference paper that we submitted to ICPP 20, we examined the efficacy of the current state-of-the-art of the GPU software stack for sparse and dense linear algebra in porting our CPU implementation of SISLICE to the GPU. But instead of examining the performance of the GPU implementation of SISLICE into some application code, we chose to develop a proxy application which probes the performance of our GPU port of SISLICE, but in a reproducible setting. As the strong scaling limit of SISLICE is achieved when each spectral slice may be treated independently on some process grid, the performance of SISLICE may be reasonably characterized by measuring the time it takes to perform a single set of Shift-Invert subspace iteration, followed by some estimate of the time it takes to perform the synchronization between independent spectral slices. As was previously discussed, the overall time that it takes to perform the synchronization step in SISLICE is essentially negligible relative to the computation time required for the diagonalization at every SCF iteration. So in this work, we just approximate it by simply adding a second onto the computation time for the Shift-Invert subspace iterations. Given this scheme for our proxy application, there are really three limiting cases for our implementation of the Shift-Invert subspace iteration given the current state of the GPU software stack for sparse and dense linear algebra. The first two cases deal with dense matrices in that they can be performed either in shared or distributed memory. In the context of sparse matrices, we're going to limit our discussion of GPU implementations of the Shift-Invert subspace iteration to use the SuperLU or SuperLU dist library. Because SuperLU dist is a distributed memory sparse linear solver, we do not make the distinction between shared and distributed memory sparse Shift-Invert subspace iteration in this talk. For the shared memory implementation of dense Shift-Invert subspace iteration, we chose to examine the performance differences both of the individual kernels of the Shift-Invert subspace iteration as well as aggregate timings for a GPU implementation targeting the NVIDIA Tesla V100 and an array of CPU implementations targeting a representative cross-section of contemporary high-performance CPUs using vendor-optimized LAPACK and BLAS implementations for the various architectures. In the table here on the bottom left, we're able to see that with the exception of the triangular factorization and the Kolesky QR step, we're able to exhibit larger speedups for larger problems, i.e. n greater than 10,000, than for smaller problems. This is due to the fact that we're able to express more concurrency on the GPU using cuSelver and cuBLAS for these larger problems than for the smaller problems. In aggregate, we're able to obtain roughly a 4x improvement in the Shift-Invert subspace iteration over the fastest CPU implementation for large problems, and about a 1.5 to 2x improvement for the smaller problems. In addition to making performance comparisons between the CPU and GPU implementations of Shift-Invert subspace iteration, we chose to examine the aggregate proxy application performance characterization with both CPU and GPU optimized implementations of dense eigenvalue decomposition in shared memory as well. The GPU implementation of Shift-Invert subspace iteration outperformed the shared memory eigensolver and cuSolver by a factor of 9 and the fastest shared memory CPU implementation on the Xeon Gold processor by a factor of 25. Due to the fact that SISLICE is a distributed memory eigensolver, in addition to making comparisons with a shared memory dense direct eigensolver, we also compared with various distributed memory dense eigensolvers to examine the extent to which this is efficacious in the strong scaling limit. Our GPU implementation of the proxy application was able to outperform the fastest distributed memory CPU eigensolver in the ALPA library by about a factor of 44, and the distributed memory GPU eigensolver in the ALPA library by a factor of 11. For the distributed memory implementations of dense Shift-Invert subspace iteration, we have made analogous comparisons using the Slate library for the GPU implementation of the Shift-Invert SISUBIT iteration, and the Scala-Pack and ELPA implementations for the distributed memory operations. As we can see here from the figure on the top left, our GPU implementation of the Shift-Invert SISUBIT iteration using the Slate library is able to outperform the analogous CPU implementation at low processor counts, but exhibits a poor strong scaling with increasing number of processors. This stagnation in strong scaling for the Shift-Invert SISUBIT iteration based on the Slate library is likely due to a decrease in work on the individual processors, thus leading to less potential concurrency being able to express on the GPU before communication between the nodes performing the Shift-Invert SISUBIT iteration. Much like the shared memory performance comparisons made in the previous slide, we compared the performance of the GPU and CPU implementations of the Shift-Invert SISUBIT iteration with analogous distributed memory dense eigensolvers in the Scala-Pack and ELPA libraries, including the GPU implementations in the ELPA library. Our implementation of distributed memory Shift-Invert SISUBIT iteration using Slate was able to outperform the fastest CPU distributed memory eigensolver in ELPA by a factor of 1.7, but it is outperformed by the distributed memory GPU eigensolver in ELPA by about a factor of 1.4. Numerical experiments involving sparse matrices in our proxy application were performed using the gallium arsenide test matrix from the Sweet Sparse collection, which is a theoretical chemistry problem arising from a finite element discretization of the DFT equations. As of this talk, the only GPU capability in the SuperLU dist library available to the public is a GPU implementation of the sparse triangular factorization. So the sparse triangular solve, as well as the kernels involving Koleski QR and Rayleigh-Ritz, are still performed on the CPU for these sparse experiments. As this gallium arsenide test case is a symmetric problem, and SuperLU is an LU factorization, we also included reference timings for using the Paradiso library, which are here in the dashed horizontal lines labeled blue and red for the triangular factorizations and triangular solves, respectively, just for posterity. Much like the dense distributed memory implementation in the previous slide, the GPU implementation in SuperLU dist of the triangular factorization exhibits poorer strong scaling than its CPU implementation. Again, this is likely due to the decreasing amount of work per processor in the strong scaling limit. However, at low processor counts, between 1 and 4 summit nodes, the GPU implementation of the triangular factorization in SuperLU dist is able to outperform the CPU implementation by about 10%. Much like the dense experiments in the previous slides, we compared the performance of our proxy application using SuperLU dist with the analogous implementations in the direct dense eigensolvers in Scala-Pack and ELPA. For the timings presented here in the figure on the top left, the sparse timings using SuperLU dist were obtained using a single summit node, whereas the numbers for the dense eigensolvers are obtained using a 32 by 42 processor grids over 32 summit nodes. Overall, the sparse implementation of the GPU Shift-Invert SISUBIT iteration using SuperLU dist was able to outperform the fastest CPU dense eigensolver by about a factor of 4.1 and the fastest GPU eigensolver by about a factor of 1.4. So in conclusion, there are really two positive takeaways that we can take from this work. And the first is that for matrices that can occupy the memory space of a single compute node, whether that be a sparse or a dense matrix, porting the compute-intensive kernels of the SI-SLICE method over to the GPU yield pretty decent performance improvements over the CPU implementations of both SI-SLICE as well as dense eigensolvers both in the CPU and the GPU. The second is that even though the GPU implementation of the dense eigensolver in ELPA was able to outperform our GPU implementation of SI-SLICE with the Slate library, these libraries are still very much in their infancy compared to the shared memory implementations of GPU, linear algebra, and distributed memory CPU implementations, etc. So further improvements in the distributed memory GPU, linear algebra software stack will likely yield drastic improvements in this implementation in years to come. Thank you for listening to my talk, and I hope you enjoy the rest of the conference.